So good morning all. What you are going to see over on it, Abhina, we are going to see about and what are all the typical max execution cycles. Okay. So in order to obtain the sample of the input signal, we have to move the input sample into the input buffer. It has to fetch the coefficient from internal buffer, multiply the input sample by the coefficient, and also add the product to the accumulator. Move the output to the output buffer, send it out as a sample of the output signal. So these are about the execution hardware. So we'll have a program counter, data read address, data write address, data memory, accumulators, CPU, program coefficients are the memory. So the next thing we have to see about an architecture of signal process. So general purpose software which is based on one human architecture. So they'll have a single memory bank and processor access this memory bank through a single set of address and data lines. So hardware architecture which is commonly used in DSP processors. Separate data and program memory. So we'll have a two memory banks over on it. Separate address buses for data and program memories over on it. Okay. Additional features in the DSP processors are instructional cache and pipeline processor as in many modern microprocessors, but no data cache. Separate ALU, multiplayer, and shifter connected to multiple internal data buses, which are enabling fast max data operations. Whereas they have a DSP processors cannot be called truly as a RISC type of processors. Some features present in the RISC processors may exist. However, DSP processors are turned towards operations encountered in signal processing applications. What about the DSP implementation approaches? So we'll have an important desirable characteristics. One to be the adequate word length, second one to be the fast multiply and accumulate, third one to be the high speed RAM, fourth one to be the fast coefficient table addressing, and the last one to be the fast new sample fetch mechanism. What about the DSP functions implemented with IC chips? So the uses which is to have over on it about speed features. So accuracy, length, and floating point capability. So cost VLSI advances in VLSI techniques. So we'll have a speed, architectural features, accuracy, and then we'll have a register length and the floating point capability. Cast. So we'll have advances in VLSI techniques over on it. So what are all the general purposes of DSP features? The first thing to be the it have a parallelism functional unit. So that is, we'll have a parallelism. That is, it has a multiple functional units, or it has a multiple buses, or it has a multiple memories. Second one, it will have a pipeline. Third one to be the will have a one hardware multipliers and other arithmetic functions. And the fourth one to be the will have often on chip and cache memory. Fifth one to be the it has a variety of addressing modes. Sixth one to be the will have often instructions that have pack often several operations. The next one to be the zero overhead looping. Next, that to be the IO features such as interrupt, serial, IO, or an DMA. And the last one to be the other control functions such as states will have over on. Okay. The next to be the what about the second order FAR filter? So when you are saying second order, the first the input to be the x of n. So the correspondence output to be the h of 0, x of n minus 1. So h of 1 x of n minus 2, h of 2. So output will be giving of an y of n over on n. So y of n is equivalent to h of naught into x of n plus h of 1 into x of n minus 1 plus h of 2 x of n minus 2. So for the case of an n minus 1, we'll use of a delay element over here. In order to multiplication, we'll use a multiplier. In order to add two symbols, we'll have a piece of an adder over on it. So this is the way to implement as a second order FAR filter. So when you are saying about the organization of or signal samples and filter coefficients for an FAR filter implementations, so we'll have of one x of n plus 1, so which is given over here, just given to the delay, and then finally we'll have over on it. So all these things it is combined over in the math model in order to give the output of an y of n over here. So how to have of an nth order FAR filter implementation? So in the case of an nth order FAR filter implementation, we'll have of an a of 0, a of 1, a of 2, and then finally we'll have of an a of n minus 1. So which all these things which is necessary over here to be an coefficient memory. Whereas in the case of an x of n, x of n minus 1, x of n minus 2 up to y of n, we'll have of an data memory. So everything which will be stored in the case of an accumulator. What about FIR filter pseudocode? So we'll have of an load loop count, initialize coefficients in data address registers, zero accumulator and feed registers. So when you are writing of an loop over here, so we'll have of an p new that is equivalents to a of I dot of x of n minus I accumulator new is equivalents to. So we'll have of an old accumulator plus your old value decrement coefficients and data address registers. So which is to be for the next iterations, which is cover over here x of n minus I, x of n minus I minus 1. So we have to decrease the loop count. So before non-zero loop, and then finally it has to be given to an accumulator in order to get the value of an A of n. What about the typical DSP architecture? So we'll have often program memory, data memory. So in between that, we'll have a program memory address, data memory address. So we'll have instructions and secondary data. So whereas the data addresses generators, so we'll have often, then it has to be given to an program sequencer. Similarly, it has to be passes over to an register cache. So we know that all the addresses has to be stored in a register that has to be given to an multiplier. We'll have often ALU, shifter, we'll have often DMA bus, and then we'll have a IO controller. Finally, we'll have often input or an output over on it. So what are all the salient features which is present over here? We'll have often repeat math instruction which has to be performed auto increment of both coefficient and data printers, frees up program memory bus for fetching coefficients, and then we'll have often circular buffer in order to manage data movement at the end of the every output computation. It will have a handling precisions in order to have often accumulator guard bits, saturation modes, and we'll have often shifters which is of both from right and left shift. And then what are all the types of multipliers which is used over here? So we'll have often array multipliers and the multipliers based on modified Booth's algorithm. What about the product computations unit of a single multiplier for 4-bit unsigned numbers and x and y? So when you are saying about over here, the multiplications which is summation, we'll have often process over here. So carry out. So we'll have often A, B, C. So this is to be when you are adding up of 3 bits over here, it will be given to over here sum, and then we'll have often carry. The same process just carried over here in order to give often multiple inputs in order to produce a when we are making an addition of 3 bits or when we are making addition of 2 bits, we'll get the output as an sum and your carry. So if you are adding often 2 bits 0 and 0, the sum will be on 0. The carry will also be in 0. But in the case of when we are making often 0 and 1, sum will be 1, carry will be 0. Similarly, when we are making often 1 and 0, the sum will be 0 and the carry will be 1. But in the case of an adding of an 2 1, so what will happen? So the sum will be a 0 and the carry has to be over on a 1 over here. At the case merely when we are adding up of an 3 bits, that is 1 1 1, what will happen? The sum will also be 1 and the carry will also be 1 over here. There is a type of an full adder or an half adder circuit over here. So that is used over in the case of an summation unit with a simple multiplier. Okay. So what about in the case of an Booth algorithm? So we'll have often 1-bit adder or subtractor. So the thing is to be that we'll have often so the carry out. So in the case of an so it, at the same time it is added which the circuit shows here to be that either we can be used as an 1-bit adder or 1-bit subtractor over there. Okay. So for the case of an for 1 and 0, we have to make an addition. That is the output will be an addition A plus B plus C. Whereas in the case of an 1 and 1, if the H and B are to be 1 and 1, we have to do the subtractions over here A minus B minus C. Okay, so this is the case of an when you are using over here. Similarly, if the H is to be 0 and if the D is to be don't care, that is either to be an 1 or an 0, that is the thing is to be that simply the value of A alone. Okay, so we'll based on the H and D value. This is the Booth algorithm says that. That is the H and D decides whether we have to perform adder or an subtractor or it will performing an no operations over. Okay. So far the thing is to be that how the architectures, so we'll have often one human architecture and Harvard architectures, and what about the instructions we'll have over on it. So everything which is based on the goods algorithm, the algorithm which decides that based on the value of an H and D in order to perform of an addition or an subtraction over here. So the next thing we can see in the next class. Thank you.